let's start looking at covalent compounds a little bit. And again, we should know that a covalent bond involves the sharing of electrons. This is a case where I can't give both atoms a full outer shell by transferring electrons, so sharing seems to be the best option. Ionic compounds will always involve a metal bonded to a nonmetal. Covalents are all nonmetals, and to be honest with you, the rest of the study guide we're really focusing on covalent compounds, so you're really only looking at a very small section of the periodic table when you think about covalent compounds. We're only focused on nonmetals. Now, just like there are energy changes involved in the formation of an ionic compound, there are also some energy changes involved in the formation of a covalent compound. Now, this first statement is true of any bond. Any bond will form when the atoms are at a lower, more stable energy level, which is usually the case. I mean, the only atoms on the periodic table that don't need to bond are the noble gases. They already come with full outer shells of electrons, which is stable. Everybody else needs to either gain electrons, lose electrons, or share electrons so that we can have a full outer shell, which means that we're at a lower, stable energy level. So that's kind of the octet rule, that we're looking to fill the outer shell usually with 8 electrons, unless we're like a small atom, and in that case maybe we're only trying to fill the first energy level, which would involve 2 electrons. Okay, so when we form a covalent compound, it says here, atoms will arrange themselves at a distance that minimizes repulsive forces and maximizes or optimizes attractive forces. Somebody asked once, when you think about it, I get it that atoms would want to bond, they want to fill their outer shells and blah blah blah. But they'd said to me, what if you have 2 atoms and you start bringing them close to each other? Like here we've got these little awkward sketches of hydrogen atoms. What if I start bringing that hydrogen atom close to another hydrogen atom? Wouldn't there be a little repulsion? Or it could be any atom for that case. The first thing that interact would be like the electron clouds, right? Both atoms are surrounded by negative electrons. And so they'd say, if you start bringing these atoms close to each other, won't they repel? I get it that eventually, there's a positive nucleus that will be attracted to the negative electrons in one atom and another. But initially, yes, there are some repulsive forces. And often it is like repulsion of the negative electron clouds, and there could be some repulsion from the 2 positive nuclei. So we have to bring these atoms together and find this perfect distance where we optimize the attraction that can occur between the electron clouds and the nuclei and try to minimize the repulsion of light charged particles. This perfect distance is called the bond length. It's measured as kind of the distance between the 2 nuclei. Okay, so here's this beautiful little graph. I would be familiar with something like this. I could almost promise that you might see something like this on the AP test. So here's what we got. We're talking hydrogen in this case. The graph measures 2 things. One of them, internuclear distance. The distance between the 2 nuclei measured in nanometers. Yikes, that's small. On the other axis, we're measuring energy. And we could be more specific and call it bond energy, the energy either required to break the bond, or we could think about it as the energy released when the bond forms. It's the same energy value. The difference is just the direction of the energy flow. Are we releasing energy to form the bond or adding energy to break the bond? Now initially I've got these 2 hydrogen atoms and they're pretty far apart. They're at a distance where there's really no interaction yet. Let's write that in. Right here there's no interaction. So if I kind of followed across, the energy level is about 0. They're too far apart. As I start bringing those hydrogen atoms together, notice the energy level drops. It's okay, here they come. Ooh, I like this concept. You got an electron, I got an electron. What if we share those electrons and we can both have a full outer shell of 2? Because we're just trying to fill the first outer shell with hydrogen, right? Okay, so we have to find this perfect distance where we optimize the attractive forces and we minimize the repulsive forces. That perfect distance should occur at the lowest energy level. Low energy always represents the most stable state for whatever particles are involved. So that bottom peak, I guess you could call it, that should represent your bond length. Internuclear distance, the perfect distance between the 2 nuclei, there's your bond length. Ah, cool. 0.074 nanometers. So there's one thing they could ask you about a graph like this. Obviously, they wouldn't have it written in there, like hydrogen bond length. But they might say, like, hey, for this random molecule, whatever it is, what's the bond length? And I should know that that's the lowest energy level. That represents the distance with the least repulsive forces and the most attractive forces. Now, the other thing that's important, okay, so I find the lowest energy level, follow it down to get the bond length, follow it across. Here's the amount of energy released when that bond forms. So when we form the bond, we release 458 kilojoules per mole. So let's say when we form the hydrogen bond, delta H is negative 458 kilojoules per mole. We release 458 kilojoules per mole. However, we should also make note that if you want to break the bond, if you want to break the H2 bond, delta H is just positive 458 kilojoules per mole. By definition, that's called bond energy, the energy required to break a bond. Now, what if they asked you that off of this graph? Hey, how much energy is required to break the bond? And you're like, well, wait a second. How come that energy value is listed as a negative? Well, on this particular graph, we're plotting energy released when that hydrogen bond forms, which is an exothermic value. But I should know then that in order to break the bond, I just have to add that same amount of energy back. Cool. So the most important point on this graph is that point where you've got the lowest energy level. That's where you'll find the bond energy, the energy released when the bond forms, and the bond length. Now notice too, if I start bringing those 2 hydrogen atoms too close, yikes, too close. Look what happens to the energy level. Now it increases. If we're at a high energy level, that's unstable. We don't want that, right? So we're really only concerned with the lowest, most stable energy level on a graph like this. I can almost promise you that you'll see something like this on the AP test. And if you do, time for a fist pump, because it's really easy. You'd crush it.